Hey guys, you're watching Python tutorial videos on my YouTube channel, Python for Microscopists. In today's tutorial, let's have a look at topology of deep neural networks. In fact, this should have been the first one of my first videos, but it's never too late. Now, well, in case you don't know what topology is basically how various components, of some system or something, are interrelated and arranged. So we're talking about deep learning. So what we mean is how our various components of our deep neural networks are interrelated and arranged. Now let's actually build our model, okay, from scratch. Well, we'll be copying stuff from somewhere, but then at least let's go through the thought process of building the model, okay? Now, for that, the first question you typically ask is your challenge a regression problem, a multi-class, or a binary classification, or a multi-channel? So there are various, or natural language processing. So when we say deep neural networks, it's pretty broad, right? So first of all, you have to pin it down to what example it is. Now, in case you don't know what is multi-label, multi-class, maybe I'll create a bunch of videos on each of this topic, and then possibly explain each of them using a specific example. But for today, let's actually focus on multi-class challenge, because I think that's probably a very intuitive and easy example, because we would be classifying a dog as a dog, a cat as a cat, an airplane as an airplane using our CFAR10 data set. Okay, so let's jump in and not talk much, but actually see a lot of code. Well, when I say a lot, don't be intimidated, but relevant code. Okay, so first of all, before you create your model, the first thing you do is, by default, I usually import a whole bunch of keras. I like to work with keras, okay? So I import a whole bunch of keras, libraries that are, or modules that are important, like convolutional 2D layers, because we need to create convolutional 2D operations, max pooling, dense, and flatten, okay? Dense for the dense layers and so on. And I'm importing CFAR10, CIFAR10 dataset, and this is the one where you have about, I think, 60,000 images. Each image is 32 by 32 pixel size, and you have about 10 labels, including cat, dog, airplane, and a whole bunch of others, okay? Go ahead and Google that, search for that if you want more information. Now, I'm also importing normalize, two categorical, dropout, and again, I talked about these in one of my previous tutorials about the importance of normalizing your data, batch normalizing your data, and then so on, okay? And also optimizers, I'm importing stochastic gradient descent. Now you can use a bunch of other optimizers like Adam. Again, I'm prepared videos on this, so I don't want to talk about each of this aspect, but I assume that you have a knowledge of, okay, so these things exist as my tools. How do I arrange them? So the first challenge is let's actually get inspiration from an existing architecture. And for any of these classification problems, like VGG can be a great inspiration. Okay, just Google search for VGG 16. And you can see, you can actually even get your hands onto some of these code out there. There's a lot of code on GitHub. But for now, I just want to understand the topology here, okay? Which is, okay, you have convolutional layer one, right? So within this, there are within this block, there are two convolutional layers, and then max pooling. Two convolutional layers and then pooling, and then three convolutional layers and pooling. Okay, that gives me a good starting point. So let's come down here. And now let's start by importing the data and understanding the data, okay? So actually, I have created, let me go ahead and copy some lines of code. So let's import this so I don't waste your time, basically. So the way you import this data set is by running these lines, right? So now we have our X-train, Y-train, X-test, and Y-test, which is loaded from our CFAR10 dataset, which is already part of this. Now, obviously, if you're loading your own data, then go ahead and load your data and then separate it into training and testing. So, okay, using, again, that's the technique. We know how to do it. So this is also key part of our topology, right? I mean, this doesn't define the model, but it defines that, okay, you need to separate your data into train and validation or test data sets so you can validate it. If you have a different data set altogether for validation, fine. Okay, so that part you need to understand. So let's go ahead and plot the first few images to have a quick look at exactly what we're dealing with. Okay, so here again, these are 32 by 32 pixels, so it's not always clear what they are, but in this case I see some sort of a bird here, a horse, boat, I don't know, that looks like a frog, and a bus and truck, car, and so on. Okay, and again, you can go ahead and study, you know, what else is there. I see airplanes, automobiles, birds, and cat, deer, dog, frog, and so on. Okay, so once we have this, let's remove the lines about plotting. This is only to understanding. Again, I'll share the code with you, so don't worry, don't bother freezing the screen and writing down or something. So I want you to pay attention to how the thought process is here. Step one, I want my data to be ready. Okay, it's ready right now. Step two, well, the data is imported, but is it actually normalized? If you actually look up here, my xtrain and right there is 32 by 32 by 3. If you look at the values, these are all unsigned integer 8 going from 0 to 255, because these are all 8-bit images. Yeah, pixel value goes from 0 to 255. And I did talk about the importance of scaling and normalization in my previous tutorial. So let's start by normalizing this data. And how do we do that? Again, we imported the normalize. I mean, there are multiple ways to do in that. One is just to take your xtrain and divide by 255. You're all set. But I'm actually using this normalize right here that I imported from keras.utils. And then I'm just applying the normalize over there. Okay, so that's step one. Now, again, we are doing this multi-class problem. So if you look at your Y train or Y test, if you look at this, this is like one single column of values ranging from 0 to 9. This is not ideal for your classification. You want these data to be in a categorical format. Again, I made a video. Go ahead and watch that about what does that actually mean. But let's go ahead and run this and look at the output so you get an idea of how that looks like. So now if you look at this, for each of these categories, 0 through 9, you have this one hot encoded, which means only one pixel has a value of 1 and everything else should be 0 in that row. Okay, so that's one hot encoding, meaning this image is whatever that label 1 is, this image is that label. Okay, that's what that's basically telling us. So this is how the input looks like. Okay, so now we have our input ready. Now let's go ahead and try to implement this, define our model. Okay, so first let's actually do only the first block, which is 2 convolutions and pooling. And then let's take a couple of dense layers. Okay, so how do we do that? And again, I have written a few lines of code so you don't waste your time. Now coming down, and there you go. Okay, so what did I do? I defined 2 convolutional layers and a max pooling, and then 2 dense layers. Okay, that's exactly what we're doing. 2 convolutional, pooling, and then, well, you could add another dense if you want, but I'm just doing 2 for now. Okay, now I started with, again, you can experiment with any numbers right there. Okay, you can try 16. I am taking inspiration from VGG. By the way, if you just copy directly the VGG architecture, I believe they require images in 242 by 242 pixel size, I think, for their input if you use their own architecture. But feel free to change these and then see how that affects. I usually leave my kernel size to be 3 by 3 right here, and then 2 by 2 for max pooling. Okay, for convolution 3 by 3, and for max pooling 2 by 2. And also for activation, again, I talked about this in the previous tutorial. For activation, let's go ahead and use ReLU for the hidden layers, and for these, the final one, I'm going to use softmax because, again, multi-class problem. If it is a binary, then it would be sigmoid, for example, or even for other regression type of analysis, maybe other type of activations. But for multi-class problem, always try to use softmax. Again, experiment with others if you want. Now, kernel initializer is HE uniform is a good one. Again, this is kernel initializer is basically, it initializes the weights. The better the initialization is, or the closer the initial weights are to the real answer, the faster this training happens, right? So that's what that is. And my input shape is 32 by 32 by 3. So that's and it's 32 by 32 by 3 because my images are already 32 by 32. If not, you may have to add another step here to resize your images, right, to the right size. And I've done this in many of my previous tutorials. Again, I'm not going to waste your time talking about that stuff. Okay, so we have this, and then the dense layers. And before the dense layers, obviously you're going to flatten it, because dense layers means convolution is two-dimensional and dense layers is one-dimensional. Think of it that way. Okay, so you're flattening all your two-dimensional information into 1D right there. And then I'm doing 128, and always the output, the final layer, should have the same number of outputs as your predictions, as your number of classes. So we have 10 different classes here in this data set, so my output is going to be 10 here. Okay, and we are using softmax, and again, softmax, if I remember right, softmax actually outputs probability of each of these dense layers, thinking that this is mutually exclusive, meaning if it is a cat, it cannot be a dog, right? So that's the way the probability is, and when you add all the probabilities, it should add up to 1. I think that's how softmax works. Sigmoid, on the other hand, it gives you probability, so it can be by thinking that it's not mutually exclusive. Okay, so the probabilities do not add up to 1, but it tells you that, hey, this image is probably 0.6% or 60% dog or 30% cat, and so on. Okay, and so after defining this, I'm going to define my optimizer as a stochastic gradient descent with a learning rate of 0.001 and a momentum of 0.9. And again, momentum defines how fast you're training, and again, momentum is the push that it gives in case you have local minima. Okay, again, watch my tutorial previous to for most of these questions that you may have when I'm talking about this, the answer is probably lying in one of my previous tutorials. That's my way of marketing my own videos. Go ahead and watch those other tutorials, because I cannot just keep talking about every little aspect in every video, then it makes every video to be boringly long. Okay, I bet this is already getting boringly long for you guys, some of you guys. Okay, so this is the optimizer I'm using. Also experiment with other optimizers like Adam, for example, is a great optimizer that I use. And what loss to monitor, what loss function are you using? I'm going to use categorical cross entropy, because this is a multi-class problem. For binary, it would be binary cross entropy. And for regression, it can be mean squared error and some others. And metrics to track for each epoch, I'm tracking accuracy, so I can go ahead and plot the validation accuracy and the train accuracy. So this is it. This is my model. I defined it. Now let's go ahead and fit our data to this specific model. And how do you do that? And before even jumping into that, I am going to create, again, I'm going to use all the stuff that I talked about in the past in this video. So I'm gonna, which makes it, if you have time only for one video, maybe this is good enough. Okay, so let's separate this. So here I'm going to use data augmentation. So I'm going to randomly, again, this improves your training. So this is my data augmentation step. So my model.fit is basically model.fit. Let's go ahead and copy those lines. In fact, we do not need data augmentation here. I'm just including it so you know about it. As you can see, I'm basically training it on my X train and Y train. So let's not do this then. Okay, let's not do that. And sorry, I keep changing my mind when I because this actually does a great job. Let's actually use it. And sorry, this is model 1, right? How do we fit a model? What is our model name? Model 1 dot fit. But since I want to use my generator here, I'm going to change this on the fly, and hopefully there's no issues here. Model dot fit underscore generator. Okay, fit generator, which means I'm not going to give it X train and Y train. I'm just going to give it the generator. So I'm going to just say train underscore, where is my generator? Train underscore generator. That's what I called it. Okay, this is the image, that generator that's supplying images while it's training. Okay, I'm not doing data gen, saving images to my folder, but I'm generating it on the fly. Okay, so let's go ahead and do this part, and then my number of epochs for now, let's go ahead and do this. And instead of batch size, because we are actually, let's remove all of this. Sorry about changing these, but at least you'll learn. Let's actually do batch size. Okay, and let's do 32. Okay, so I think that should do. Batch size, oh sorry, not batch size, I wanted to do steps per epochs. Steps, I think this is how you define it. Steps per epoch equals to, let's just do 500 for now. Okay, steps per epoch, and we have this. And by the way, if you want, you can actually include your validation data here. Okay, so let's go ahead, and I shouldn't have deleted that. Validation data, you can hold out part of this as validation data, when you're defining your inputs, but since we already have our test, let's go ahead and do that. Validation data is let's see, X, did I use uppercase, X test and Y underscore test. Okay, I have a feeling this is going to be a very large video, long video I should say, and let me put everything into one screen so you guys can see it. Okay, X underscore test. Oh, God, X underscore test. And why is it yelling at me? Yeah, it's there, X underscore test and Y underscore test. That's what we are going to use, X, Y. Okay, so that works fine. And then we can evaluate model later. Okay, so we haven't still talked a lot about topology yet, but we'll get there in the next few minutes. Okay, for that, I'll just go ahead and copy and paste, but this part I wanted to go a bit slow. Okay, so so let's go ahead and look at model.1, evaluate after it's done. Okay, how do we evaluate it? Model.1, evaluate X test and Y test. Let's just look at our accuracy values. There's a lot more you can do, but let's just go ahead and plot. Let's go ahead and plot our curves. Again, this is something I do with every part of my training process. I know I can hear you guys forwarding my video for sure because it's getting long, but I'm glad you are still sticking through. Okay, so this is it. So what have we done? We defined our model. We gave it a name called model 1 because I want to add model 3, model 5. In this model, 2 convolutions and 2 dense, and then we are using stochastic gradient descent, and I'm using the generator to actually to provide my inputs to this. And then let's only do 10 epochs. Okay, so we can look at the results. And finally, I'm actually printing out the accuracy by multiplying my model.evaluate value by 100%. So to look at this, and I'm plotting my loss, training loss and validation loss, and training accuracy and validation accuracy. This is it. So let's go ahead and run this. Okay, so let's have a quick look at this. So the final accuracy is 42.47%, not great, obviously. And the good news is these two seem to be doing fine. You see the training loss is coming down, the validation loss is also doing a good job, and then the validation accuracy is improving, and the training accuracy. It's interesting that the validation accuracy is higher than the training accuracy, and I'll let you investigate why that could be the case. But usually the validation is lower than the training accuracy. Okay, so now again I'll pause the next part of the training, but what I would like to do is now let's actually add I'll share the code again. So let's actually add this part. So what I'm doing is removing this model and adding a different model. Again, it seems like a lot of stuff going on, but in this example what I've done is defining the first 3 of these blocks. Yeah, 2 convolutions pooling, 2 convolutions pooling, and 3 convolutions and pooling. That's exactly what you see here. 2 convolutions pooling, 2 convolutions pooling, 3 pooling. Everything else I left the same. Okay, so now model 3. So let's go ahead and change this to, instead, in fact I should have just used model. Okay, so model 3, and I think that should do. And I'll run this again. I'll pause the video, and then we can have a look at the result. Okay, so I'm hoping for a higher accuracy than 42.47. So let's go ahead and see that. So let's run this, and I'll pause the video. Okay, so here it is. So we got 47.22. Not, again, some improvement compared to earlier, but not as much. And the fact that again the validation is higher than training accuracy tells me that it's still trying to train it a bit better. In fact, if you let it go for like 300, 400 epochs, you can see that, okay, the training is eventually getting better. And also maybe I could have supplied a lot more images to training, but let's not worry about that. Let's not change the experiment right now. But one thing that let's do is see if dropout has an effect. Okay, so here I'm actually adding dropout. Again, I talked about dropout in one of my previous tutorials. The importance of dropout prevents overfitting. Okay, although that's not the case in our case, at least not clearly visible. But let's exactly the same as before the previous model. Now I'm actually adding dropout of 20% to each of these layers. Again, this is the topology that I'm talking about. Okay, what happens when you add something, when you not add something? Of course, there's research going on from a fundamental point of view to understand exactly the effect of each of these. But again, depends completely on the type of challenge that you're working on. So let's go ahead and run this. Again, I'll pause the video and let's look at the results. Well, that definitely did not seem to improve. Again, here are the curves, and it's 43.18%. And by the way, halfway through this, I realized that, okay, I didn't change the model name, so I changed it to model 3 drop, which is the right one, right, where we are using dropout, and I cleared all the variables, so no effect from the previous runs is on this data. So let's do this final thing. And dropout, again, go ahead and try it on your data sets. Now here I'm doing the whole bit. Now I'm doing dropout, but more importantly, I'm doing batch normalization. I hope this has a huge effect, because typically, again, I should have practiced this, but this is the first time I'm doing while I'm training here, while I'm teaching on the camera. So I'll be equally surprised or not surprised with the results. Okay, so batch normalization for each convolutional layer right there. Okay. And I seriously hope that this is going to help out. Okay, so batch normalization always lives up to expectations. So let me copy this name so I don't repeat the same mistake I did earlier. So let's go ahead and do that. Batch normalization. Okay, dropping and normalization together, and I'm going to clear all the variables over there, and let's go ahead and run this. I'll pause the video. Let's look at the results. Okay, so there you go. Let's see, some improvement, obviously 50%. It's definitely improvement. I think we are kind of dragged down by our dropout layers. I have a feeling that the dropout layers are not helping us. So this can be very addictive. I can spend a lot of time trying to change this topology and see how it affects my output. So I'll do one more thing, just drop out and then see how the results look like. But I also started to realize that my training data is so small that my validation is large. So if you want, you can actually do all 50,000 images for training and then 10,000 for testing. You'll definitely get much better results, but I don't want to spend half an hour for each of these runs as part of this tutorial, but I'll give you the code and you can try that out. So let me run one more. I'll pause the video, but I'll delete all the dropouts and I'll do one more, and let's quickly have a result, look at the result. So we can see the effect or the negative effect of dropout. Maybe there is. That's my suspicion, but let's confirm that. Okay, there you go. Now things started to look a bit more realistic, right? I mean, now you see the validation jumping up and down, and this is how it's supposed to be typically. Now we have 57.58%. So removing the dropout definitely helped a lot for us, and that's probably because my dropout was a bit more intense, right? I mean, I had initially 20% and then 40% and 50% of dropout. So it's not, I mean, for these many epochs, it's not training very well. It's not enough. Maybe we need to add a lot more epochs to actually get there to see some result. But anyway, dropout wasn't the thing for now. Now, one final thing I promise. I really do not want to use this model and then basically use the first one earlier, not by using data generator, but by using all 50,000 of my data points for X and then my 10,000 for testing purposes. I'll still do 10 epochs, but I don't know how long this is going to take. But let's go ahead and look at the result, because I have been very curious why my training loss and validation losses were a bit weird. Okay, again, I'll pause the video so it won't be a waste of your time. Just take some time from my side. So let's go ahead and run this quickly. Let's make sure model 3 dot norm, model 3 dot norm, and the only thing I changed is this part. Okay, cool. Let's run this, and then let's continue after this pause. Okay, so looks like things are looking normal with the actual data, by using the actual data. So you see how the validation accuracy, the training accuracy is near, like above 90%, and the validation accuracy is about, let's go ahead and look at it, is about 68.24%. Much better than before. Obviously, we had 57 or something, and the loss also looks almost normal. Now, you can play with the topology. Let's go ahead. I'll let you do this. Go ahead and add more of these, convolutional layers, and try to engineer the batch normalization, and maybe adding dropout now that we have a lot of data can help. But then again, our problem is not overfitting here, right? So, or maybe it is. So adding dropout can definitely help. Looks like our training is doing a much better job than validation here. So maybe it is overfitting a little bit. Yeah, maybe adding dropout definitely helps here. So there's a lot to talk about, and I can make this video much longer, but I think I should stop now. So I'll share this code. Go ahead and experiment yourself. But I hope you found this to be not just boring, because it's pretty long, I admit, but also informative. And let's again, I think in the next few tutorials, I'll start to define what regression is, and just show some examples like I promised earlier. So please stay tuned for that. And until then, please subscribe to this channel. Thank you very much for your attention and patience.